we go. All right, welcome to your 6th tutorial, everyone. Today we're going to be going over metabolism, and for those of you that was doing push-ups with me, we got some of that going, and then we're going to be going over basic features of enzymes. All right. Okay, quick review of the standard free energy. So standard conditions. We're going to have temperature is always going to be at 25 degrees, and this is going to be in kelvins. So be careful of your units when you guys are doing these calculations, because often you might get the temperature in Celsius, and it might be 37 degrees if you're not at standard conditions. So remember that you have to convert it to kelvins. Pressure, pH, and then your substrates at standard conditions are going to be 1 molar of your substrate product. Again, be careful with units. A lot of the time you are going to be given your units in like millimolar or micromolar, so you do have to convert those. Our normal equation is going to be A plus B, so our subs are going to get converted C plus D. So our K equilibrium is going to be our products over our reactants. All right. Okay, quick little review. All right, hopping into our review questions. Oh my God, I'm actually like out of breath. Define our delta G standard and our delta G, and how can we represent those mathematically? Standard free energy, standard conditions, yes. And our delta G is yes, our Gibbs. So our kind of physiological or whatever conditions are in the environment. And then we can also represent this mathematically. So our standard free energy equals our negative R times temperature, and then the ln of our K equilibrium. And then Gibbs free energy is a change in the system. So you can have cellular or like any concentration really of our substrates or products in order to determine the Gibbs free energy. All right, review. If we have a lot more products than substrates, our K equilibrium is going to be greater than 1. What does this tell us, or how is this going to convert to our standard free energy? Nice. Exergonic, negative, favorable, spontaneous, all the things, yes. So we're going to have a negative delta G, and this is going to be spontaneous. What about a K equilibrium less than 1? Positive, perfect. And this kind of goes back to our ln. So our ln of a decimal is going to be positive. And then what happens if our, and then you guys are also saying not spontaneous, needs energy. If it equals 1, people are saying reversible, yes. 0, reversible, awesome. So ln of 1 is 0, so it could go either way. It could be really pushed in any direction. Nice. All right, if you are looking at succinate dehydrogenase and it has a standard free energy of 0, which value below is closest to our standard conditions? Let me just put up a quick poll. D. There we go. Beauty, you guys are on the ball this morning. The answer would be 1. It's all those push-ups you guys did prior to class. Got your blood flowing. All right. So the answer is 1. Remember, the ln of 1 is 0. All right. Okay. Where do we actually get this energy from? ATP is our major carrier of chemical energy. So just a review of our structure is we have these 3 phosphate groups, and the cleavage of these high energy bonds is what kind of releases energy, and this is what's going to power other reactions and allow them to go forward. So we have our 3 ATPs, and most of the time we're going to cleave off the 3rd ATP, and then we're going to get 2 phosphates, so we're going to have our ADP. And then we're normally going to have a magnesium ion stabilizing this. So I feel like a lot of you guys saw this in your enzyme assignment, where you had a magnesium ion coordinating these phosphates, and that's just to kind of help stabilize them, as there is a lot of negative charges here, which causes repulsion, which also helps with that kind of release of energy when you get cleavage, but the magnesium helps to stabilize these negative forces. So if we want to make ATP, we're going to go through the oxidative phosphorylation, where you go through the citric acid cycle, electron transport chain, in order to make ATP. But if you need kind of a quick burst of ATP, you can use phosphocreatine. So in order to make ATP from a molecule, this has to be a higher energy molecule than ATP, which phosphocreatine is. So if you're exercising, like we just did with some push-ups, you can get the conversion of ATP into ADP to kind of help with those muscle contractions. But if you need a quick burst of energy, that ADP can be converted into ATP with the addition of phosphocreatine, transferring that phosphate group back onto that ATP. Now this reaction is reversible. So that's why you sometimes hear people taking like creatine supplements if they are in the lab. Sorry, someone just asked if I drew this. I did not draw this, no. So you can sometimes hear people taking creatine supplements. So this is why they usually take the creatine beforehand, because the creatine in your body gets converted to phosphocreatine if you're in kind of low energy or you're not active. And then upon exercising, those phosphocreatine or stores that you've had in your body are going to convert the ADP to ATP to give you a little bit of extra energy. So that's kind of the basis behind that. All right, and creatine kinase is the enzyme responsible for this. All right, review question. All right, a direct measurement of the standard free energy change associated with the hydrolysis of ATP is difficult because a small amount of ATP remaining at equilibrium. So this value can be calculated indirectly using the equilibrium constants of 2 other enzymes that have less favorable equilibrium constants. So we're given 2 reactions here, glucose 6-phosphate to glucose, and ATP plus glucose to glucose 6-phosphate, using ATP. So we're giving 2 equilibrium constants, and we're actually told this is less favorable, even though these equilibrium constants are quite high. So how do we determine the standard free energy of hydrolysis of ATP? All right, we got someone coming in with the correct answer here, negative 31 kilojoules per mole. But how did you get that? What would you guys do? Find the 2 G's, yes, and then add them. Lovely. Someone said totally didn't memorize that. Yes, you could know this number off by heart, but we could also calculate it. So if you did want to calculate that, you could go ahead and plug these into our equation, the standard free energy. So I'll give you guys a second to do that. Practice putting in, the correct values and the correct units in the right spot. All right. Okay, so if you guys were to fill this out, we would get our delta G's of negative 13.8 for the hydrolysis of glucose 6-phosphate to glucose. And if we're looking at the conversion of glucose to glucose 6-phosphate, we would get negative 16.8. Someone says, why are we adding the two delta G's and not subtracting? I guess it'll depend on, like, if we're adding the reactions in this case. If you had to like flip one, you could subtract them, but for the most part, we're going to be adding the two reactions together. And if you did have to flip a reaction, just change the sign of the delta G. So, as you guys implied, we're going to couple the reactions. So you want to directionally, some students say, how do you know which kind of way to go? If we're looking for the hydrolysis of ATP, you're going to want to kind of order your reactions in the correct way, that you're going to have your final coupled reaction to form ATP. So we're going to have our glucose 6-phosphates. Those are going to cancel out, and our glucose is going to cancel out. So we're just left with ATP plus water is going to give us our ADP plus our inorganic phosphate. So we add these two values together, and we're going to get, as you guys said earlier, negative around 31 kilojoules per mole. Amazing. Okay. So, justify this statement, as I kind of alluded to earlier, that these reactions have a less favorable equilibrium constant than that of ATP hydrolysis. So if we look at these two K equilibriums on their own, they're already pretty high, considering we're looking at less than 1 or greater than 1 for being favorable. And now these are like so much greater than 1. We have 270 and 890. So how is this less favorable than that of ATP? Okay. Someone's talking about the resonance stabilization of ADP and inorganic phosphate. So that's the, I guess, kind of looking at it on a individual scale of the molecule's stability. But in terms of the K equilibrium for like the overall reaction. Okay, you guys are starting to get on the right track. The delta G for ATP hydrolysis is more negative than each of the reactions, which is correct. And then someone said the K equilibrium for ATP hydrolysis would be even higher. Yes. So it's great that you guys are comparing these. So we have minus 13 compared to like minus 30. So it's even more favorable. Higher K equilibrium means more products are made. Yes. So can we actually go and calculate what K equilibrium would be for our ATP hydrolysis? And keep in mind when you're doing this calculation that the standard free energy is going to be like minus 31. Perfect. Someone said, yeah, it's like 270,000. Yes. So you guys are correct. You have a massive, I think it's closer to, did I make a mistake in calculation? Yeah, it's up in the 200,000s. So this is much, much larger than the K equilibrium of both the other reactions. So that's why they're considered less favorable, because they have a slightly smaller K equilibrium than that of ATP. Alrighty. All right, that was one of our high energy molecules. What about our other high energy molecule, phosphocreatine? So phosphocreatine is also found in neurons to help generate ATP. Calculate the actual physiological delta G for creatine kinase. So it's giving you your temperature, your substrate concentration, and asking you to find that Gibbs free energy. Someone's saying negative 0.192. You're in the negatives, which is correct. It's going to be a slightly bigger negative. So be careful. This is one of those questions where you want to be careful of your units. Give you guys a moment to try this out. So remember also for this one, the standard free energy change of ATP with creatine kinase is going to be minus 12 kilojoules per mole, because we're going from standard free energy of creatine kinase of minus 43, subtracting that from our ATP, which is negative 31. So we're going to get minus 12 for standard free energy. So that wasn't given in the question. So that's why, sorry. But otherwise, you're on the right track with the temperature. All right, so I'll flip to the next slide. Okay. Remember, this is our Gibbs free energy, so you need to take into consideration the concentration of products, reactants, temperature, and then we're going to have the standard free value. So this is going to be negative 12 joules per mole, because the standard free energy of phosphocreatine and ATP is going to be negative 12. Because remember, our ATP free energy is minus 31, and then the free energy of phosphocreatine is going to be minus 43. So I think these were given in lecture, so that's why the review questions were kind of hoping that you go back and look at those values in order to get the standard free energy of the kind of coupled reaction to minus 12. And then you plug in your substrates, and those are going to be in molar. Oh, someone says, why couldn't you use? Yeah, I guess you could have used that too if you wanted to. A couple of different ways to approach these questions, for sure. Okay. Someone's saying, how could you use the K equilibrium? Oh, sorry, someone said, like, can you use the standard free energy equation using the K equilibrium, using the products and substrates in order to find the K equilibrium, then finding the standard free energy, and then inserting that. So you could have done that too. All right. So if you go through that, sorry guys, I was reading the comments. You can find your overall delta G is going to be negative 12 kilojoules per mole. Therefore, this is negative and a favorable reaction. So students are asking, where do you find the delta G? So you could have coupled the standard free energies of the phosphocreatine reaction and ATP hydrolysis, and those values were given in class. Or some students, I think, used the substrates and product concentrations to find the K equilibrium, to then convert that to standard free energy. Someone says, do we have to convert the units? Students are going to cancel. I would, just in case. I don't know. I don't know if it affects the lawn, if you take the lawn of that and you didn't convert them. I usually just convert them to be safe. But if yeah, okay, you got the same answer. Yeah, if the math works out, then you're good. Someone says, how do we know it's 0.001 times 0.0026? Because you're gonna put your concentration of your products over your concentration of your reactants to represent the ln of our K equilibrium. Sorry, Soon just says wait for the delta G prime. We use 1 molar for all the substrates. True. That's okay. Wait, yeah. Sorry, I think I got confused there. Yeah, I don't know if you could do that then to find the standard free energy, because then that wouldn't be at standard conditions. Yes. Sorry about that, guys. I guess I was like, oh, that is a clever way to do this. Yeah, so just correction, our delta G is going to be at standard conditions. So the concentrations I don't think work that way to find the K equilibrium at standard free energy. So I would use, for this question, guys, I would use, yeah, the standard free energies given in lecture. Yes, so someone's saying our delta G's is negative 12,000 because you're coupling phosphocreatine, which is minus 43 kilojoules per mole, and ATP, which is the minus 32. So if you couple those two, you're going to have to flip our ATP to ADP because you're producing ATP. So you're going to get that positive value. Therefore, minus 43 plus 32 is going to be negative 12. So I think if you guys, yeah, if you write out the reactions, one of them is going to have to be flipped. Yeah, okay, someone wrote it out here. Yeah, negative 42 kilojoules minus 31. So you can either do it that way, or again, if you wanted to add them, flip one of the reactions, and if you flip the reaction, therefore you have to flip the sign on the delta G. Sorry about the confusion there, guys. Yeah, so minus 43 plus 31 is going to give you negative 12 kilojoules per mole. We can then insert that into our equation, and we get a final delta G of negative 12.7. All right. Sorry, and thank you to whoever corrected me on the finding the delta G there. All right, the next part of this question is how must the concentration of substrates and products change in order to drive the reaction in the opposite direction? So first of all, how could we change that ratio? So if we have substrates going to products, just kind of in theory, how do we push that the other way if it's a reversible reaction? Increase products, yeah. So if we increase the ratio of products to substrates, if you have a reversible reaction, that's going to push the reaction towards the substrates because we have so many products. So how could we mathematically kind of show that and find that ratio? So someone's saying you guys are referring to the K equilibrium. So we could change the K equilibrium, but what about the, oh, someone put it, basically rewrite the equation as an inequality where delta G is greater than 0 and then solve. Yes. Some people are saying take delta G equals 0 and the K equilibrium for there. Awesome. So there's different ways you could do it. There's obviously, like, math isn't my strong suit, so I know there's ways to write this where you set like the delta G as greater than 0. But for this, I just kind of set delta G to 1. So you guys are great. Our delta G is negative, therefore it's spontaneous and favorable, so we would have to increase the products. Therefore, if our delta G is greater than 1 or plus 1, we would get the reverse reaction. And then, like you guys said, you can solve for the K equilibrium. So I just did this, I inputted plus 1, we have our same standard free energy, our R value, our temperature, and then we're looking at the ratio of products to reactants, and we get a ratio of 105. So I didn't calculate the exact concentrations, just kind of looked at this and said you're going to need to increase that ratio 105 times in order to flip the reaction and push the reverse reaction. Could we also use an ice table? I think the question might give you more information if they wanted like the exact concentration. But this was kind of just a more general approach. Wouldn't the creatine, yeah, I guess I wrote ATP and ADP. But yeah, if you increase the concentration of creatine as well, you'll push it the opposite way. So both the products, yeah, will have an effect. So we won't get an actual number for concentration. We'd only get the ratio. Yeah, so just for now, we're just looking at the ratio. It would be hard to kind of get the exact concentrations from these. So just a general ratio for this question was fine. All right, we're gonna get to enzymes now. So just kind of main points about enzymes is these are going to enhance the reaction rate. So they're not actually affecting this overall equilibrium. So the change here from our reactants to our products isn't going to change with the addition of an enzyme. It's just going to kind of change this, lower this overall activation energy to make this reaction more achievable. So they enhance cellular processes. And then active sites, like you can see in this enzyme here, are going to promote the proper kind of ligand binding and orientation. So this is a very kind of key point, is that our substrate needs to fit ideally in this pocket. Like I talked about earlier with the difference between ethanol and methanol, or ADH, we can have the catalytic site here in red. But the rest of the ligand does have to bind properly to that enzyme, and those contact points are going to be important for that binding. Enzymes can range in specificity, like we see again for the ADH. It is able to bind other substrates, whereas like that enzyme might be a little bit more promiscuous and then it can bind other things, where some enzymes are very, very specific to just one substrate. So that's all going to depend on the actual enzyme itself. All right, review question. Why are enzymes such large molecules, and why are active sites almost always found in clefts or depressions rather than protrusions? So it's saying clefts have more surface area to bind substrates, efficiency, more selective. Yep. Large molecules so they can stabilize intermediates. Nice. To have better binding affinity, selectivity. Excellent. Yeah, these are all great points. Just pull it up on the slide if anyone's copying these down now. So yeah, there's such large molecules to hold the ligand in that proper conformation. Like we said, you have to get selective binding of that ligand to your enzyme in the correct orientation so that that active site can have all the proper contacts. Also, it's saying it needs to form this transition state where you kind of get that intermediate between the actual ligand and your final product. And then the clefts, like you guys said, it aids in specificity. The protrusions, you wouldn't really get to get that full binding of your ligand, so that's why it's commonly found in pockets, so that you can, again, correctly orientate that ligand. Quick recap on our enzyme kinetics. We have our equation where we're going to have our enzyme plus substrate. We're going to get our enzyme substrate complex, and then that's going to convert our substrate into product and again release our free enzyme. So we're going to have the rate of formation, which is this K1, to our enzyme substrate complex, the rate of product formation, which is going to be our K2, and then we're going to have the rate of our dissociation of this enzyme substrate back to our free enzyme and substrate. So if you think about it, you're going to get substrate and enzymes coming into contact with each other. That substrate's not always going to be in the correct conformation. Again, depending on the KED, you're going to kind of get this binding and release. And then eventually it's going to be in the right orientation and get converted into our product. So the steady state assumption that's kind of driving this Michaelis-Menten kinetics is that the rate of enzyme substrate formation is going to equal the rate of dissociation. So if we write that out, we have our K1 plus our free enzyme and substrate is going to equal our K minus 1, so the dissociation of that enzyme substrate complex, plus the dissociation of that enzyme substrate to the enzyme and product. So that's why in the assumption it's saying that the breakdown of this ES complex to form product has to be slower than the formation of the ES and the breakdown of the ES to reform the free enzyme and substrate in order for these two reactions to be equal. So that's kind of the big steady state assumption, is this K2 has to be slightly slower just because of this kind of imbalance. Our Michaelis-Menten constant is going to be our K minus 1 plus K2 over K1. A student was asking earlier, is Km kind of the same as Kd? So it is looking at affinity, but it's taking into consideration this K2 value, where our Kd is just looking at our K1 and our K minus 1. So just kind of the on and off rate of our free enzyme and substrate to form this complex. Whereas this is also taking into consideration the kind of conversion to product. So that's how those two slightly differ, even though they're both looking at binding. And then we have our Michaelis-Menten equation, which you guys should definitely know, which is our initial rate is going to be equal to our Vmax times substrate over our Km plus substrate. Someone said, do coupled reactions occur sequentially, or do they happen simultaneously? I'm not, is this sorry, the question, do coupled reactions occur sequentially, or do they happen simultaneously? Is that referring to a previous question or enzyme right now? Someone says, will we always know Km? Depends. You might get asked to determine the Km in a question. It might be given. Km values, however, are going to be experimentally determined based on that initial rate. But you might be given rates, like we're going to go through, and get asked to solve the Km. Someone says, can you repeat what you said about K2 being slower? Okay, so this is part of the SATE assumption, is that the rate of formation is going to equal the rate of dissociation. The thing is, though, you're going to have two different rates of dissociation. So one of these is going to have to be like slower, if you think about it, in order for those two to equal each other. So that's why they're saying this K2, the formation of product from that enzyme substrate complex, is going to have to be slower in order for these two rates to kind of equal each other. So the breakdown of the ES product is slower than the formation of this substrate or this complex, and as well as the dissociation of this complex back to our enzyme and substrate. Oh, okay, sorry. The student that asked about this sequentially or simultaneously. I guess it depends on the reactions. So some of these are like ATP, like phosphocreatine to ATP, like those are kind of happening together. But you can take reactions that are calculated separately and then couple those together to find the free energy of that overall reaction. But it doesn't necessarily mean that like those two reactions are happening at the same time. Like those delta G's were calculated kind of like independently of each other, if that makes sense. And then those delta G values were coupled. Okay, so that's kind of the math of our enzyme kinetics, but what does this look like visually? So we have our, just kind of a little recap of our Michaelis-Menten kinetics. So we have our initial rates that are going to be calculated. So that's one thing. If you're going to have a Michaelis-Menten plot, it's always going to be your V0 over your substrate concentration. So if you have any other value here for your V0, that's not going to be your Michaelis-Menten plot. Sometimes that might come up in like quizzes or old exams. You might be given a graph, and this might be like concentration of product. And they might say like, what's the Km, but you can't really get the Km from that because it's not an MM plot. So be careful of the units on the axes. So as we increase our concentration of substrate as we go along the x-axis, we're going to get faster and faster initial rates. This is eventually going to plateau off as we get to a higher concentration of substrate, as we're saturating all those binding sites of the enzyme, and they're going to kind of hit that maximum velocity that concentration of enzyme can reach. And then we're always going to reach this Vmax, but we're never going to quite hit it. So just to review, what are these kind of values telling us? So our Vmax and our Km. Vmax is the rate at saturation. Yes, the maximum rate that enzyme can reach. And then our Km is affinity, perfect. And our Km is going to kind of equal the substrate concentration at half the maximum velocity. And yes, the lower the Km, the stronger the binding rate. So what that means is you need less substrate. So if you have a lower Km, it's saying you need less substrate to hit that half the maximum velocity. So that's why it's saying it's stronger binding, because you can get to that Vmax at a lower concentration. Half the Vmax equals Km is always true, correct? Yes. All right, next question is, prove mathematically that V naught does not equal Vmax even when substrate concentration is 20 times the Km. So if we were to plug this into our Michaelis-Menten equation, what would we get for our Vmax? So Vmax will always be lower when Km is lower, and that's why you need less substrate max. I don't know if necessarily your Vmax is going to be lower. So you can have, let's say, two enzymes that have the same maximum velocity, but one enzyme needs less substrate to kind of hit that half the Vmax. So it's saying that it has a higher binding affinity, so you're going to have less substrate, but it can bind more of that substrate to get to the same maximum velocity. So that enzyme with a lower Km and the same Vmax is going to be more efficient and have a tighter binding. Okay, yeah, so we got some students, V naught equals 20 over 21 Vmax. Yes, I think. So you guys, I think, are doing the right steps. Is we're going to have our Vmax, Km plus substrate. So our substrate concentration equals 25 Km. So we can just insert that into our substrate concentration, add those together, and we're going to get 0.95 Vmax. So it's saying that even though we're 20 times greater than that Km, we should be approaching our Vmax. We're never going to quite hit V naught equals Vmax. Our V naught is still going to equal 95% of that Vmax. How do you get 21? Because in the denominator we have Km plus 20 Km, so you have the same units, so we can add that together. So we're going to get 20 Km over 21 Km. The Km's are going to cancel. And then our 20 divided by 21 is going to give us our 0.95. Perfect. Alrighty. Okay, we have two more practice problems. Oh, we're getting into a couple homework questions, so we'll see how many we can do before noon. Next practice problem, I'll put up a poll. Refresh this. Which of the following statements is true of enzyme catalysis? Update. Here we go. To be effective, they must be present at the same concentration of their substrate. They can increase equilibrium constant, give action by 1,000-fold or more. They lower the activation energy for conversion of substrate to product. Their catalytic activity is independent of pH, and they are generally equally active on D and L isomers of a given substrate. I did not include E. It's okay, E's wrong. All right, for the most part, you guys are getting the correct answer, which is C. Perfect. A couple students said B, so remember it's not the equilibrium constant, like the overall constant of the reaction that is changing, it's the activation energy to kind of reach that equilibrium. So you're able to reach that equilibrium faster in the presence of an enzyme. They are dependent on pH, so they are very specific to pH and temperature. And enzymes don't need to be in the same concentration of your substrate. Usually you're going to have substrate in great excess to your enzyme. And then this is kind of going back to our first unit where proteins and enzymes are very, very specific to their proper enantiomer. So that is incorrect. Okay, I'm going to come back to one of the students in the chat, Christine, during our break. Sorry, I haven't read through that. Okay. Maybe I will, this question is a little bit more in depth. So I'll give you guys, if you want, during your 10-minute break, time to go over this. So Michaelis Menten enzyme catalyzes a reaction with Vmax equivalent to 9.8 times 10 to the 3 millimole per liter per minute, and a Kcat of 850 seconds. Inverse, determine the total enzyme concentration if the enzyme is comprised of 4 similar subunits, each with a molecular weight of 8 kilodaltons. Disclaimer, maybe I'll write this on the slide. Our daltons is equal to, 1 dalton is equal to 1 gram per mole. So I'll give you guys a second, and you guys can have a nice little 10-minute break here. Just take this. Is this a poll? Is each subunit catalytically active? Ooh. I'm going to say for this question, you need it to have the homotetramer in order to be active. Yes. Good question. Is this a poll? I will make it a poll for those of you for participation. Here we go. Beauty. Someone said, would this be at the end of the hour for attendance? Probably, because I was pretty early today, so I was putting up polls. But if you want to be safe, I'll put up another poll at 10 after. Kcat is also the turnover number. So catalytic efficiency. Oh, okay, thanks to the student who wrote out the map, Christine. Nice. Millimole is equal to 0.001 mole, yes. So millimole is 1,000 times. 1 Dalton is gram per mole. Thank you to the student. I'll make that a little bigger. Does anyone have any other questions? Does 12 to 10 mark the end of the hour? I think so. So I guess if class starts at, 11:10, you're gonna wanna like have participation up until 12:10. June said, Gibbs free energy, use product over substrate at equilibrium or cellular conditions. I think it's going to be cellular conditions for the Gibbs free energy. And yes, I am going to show. I'll show the math after the break. Students said if I just came, will I still be able to get participation for staying to the rest of the class? Yes. So you just need, I think, 1 hour. Yes, delta G naught prime is going to be at equilibrium. Yes, at standard conditions. So Gibbs free energy is going to be delta G naught, so your standard free energy plus, yes, your RT ln and your concentration of product over substrate on cellular conditions. Someone said their internet, connection briefly disconnected. No, I think if you kind of connect and reconnect, but you're still like overall like active for the hour, you still get participation marks. I was saying like if you just joined now, like if you weren't active for the first hour, but you're active for the second hour, you'll still get your rotation. But if your internet is kind of shoddy and you're like disconnecting, I know my internet isn't great. Hopefully it's been okay for you guys if you do disconnect and reconnect. But you're still active for about an hour, it's totally fine. You'll still get your participation grades. So once this is our break, are we still supposed to be doing the question? This is your break. So yeah, so for standard free energy, you're using 1 molar of your products and substrates. When you're putting it into the equation and determining the delta G from that at like all your standard conditions. I don't know if you'll like get asked to calculate the standard free energy of the like those values are like kind of experimentally like, determined. But you might have to like get asked to like couple them together. I'm not 100% sure on that question. I want to say they're like, experimentally you would start with your 1 molar over 1 molar of like your products to your substrates. But in terms of like, I guess what you're asking is if you were given then the concentrations at equilibrium, would you put those in? I'm not 100% sure. Like if you were to get I guess if you're asked if you're getting a question or like just maybe like how do they determine it experimentally? Oh, sorry. Yeah, you're not going to have to calculate that. Yeah. Okay, so I was getting confused with that as well. Someone said, hi, Chloe, I just joined. If I stay to the end, you'll still get your 1%. Yes. Okay, let's get this started. If you did just join, do participate in the poll to kind of start that participation. All right, so a practice problem. The tricky thing with this question was that you had to kind of convert everything. So first step is kind of doing those conversions. Where am I? Here we go. Okay, so we want to look at the total enzyme concentration, so we can get value from our kcat or our turnover number, wherever Vmax equals our kcat times our total enzyme. We can rearrange and solve for our total concentration. So you would convert your 9.8 millimole into moles per liter per minute, and then you'd want to convert your 850 seconds into minutes, so those two can cancel. And then you're going to get your 1.92 times 10 to the negative 4 moles per liter. Now the problem with this is we don't have that in our options. So you were given the molecular weight. So this was saying that you have 8 kilodaltons and you have 4 subunits. So if we use our, I put it on the other side. 1 dalton is going to equal 1 gram per mole. We can then convert this into grams per mole, so 8 times 4, and then we're going to get our 32,000 grams per mole. We could multiply the two of these by each other, cancel out our mole, and then get grams per liter, which was equivalent to our milligrams per milliliter. So the correct answer for this was actually going to be B. So this was probably one of the more trickier. This was a previous exam question. Probably one of the more trickier ones, just because there was a lot of unit conversion in it. Someone says, why did we multiply by 32? We multiplied by 32 just because we want to convert it into milligrams per milliliter, just as because that was the units that we were given in the question. So if you do this, you can cancel out the moles, and then you're just left with grams per liter. And then I showed the other conversions on the bottom here for our kcat and our Vmax to put those also into the same units. Someone's like, we have another poll. Yes. Let's just update this. Here we go, for those of you that just joined. All right. Next question. What effect would the following experimental conditions have on the kinetics, Km and Vmax in a Michaelis-Menten enzyme? Twice as much enzymes used. Actually, let me update the poll here. Multiple choice. Increase. Decrease. Update. There we go. So if we have twice as much enzyme as used, what's going to happen to the Km? Ooh, sorry, one sec. Let me update this. 1 second. Changed. There we go. Update. Try that one more time. There we go. So our Km, if we have twice as much enzyme used, okay, so we have some students saying that the Km is going to increase. So remember, Km is looking at binding affinity. So if you have twice as much enzyme, are you going to get twice as much binding to each individual enzyme? What do you guys think? Is it going to change kind of the unique binding ability of each enzyme if you have more? No. Yes. So even though you have more enzyme, this is going to affect kind of the overall rate, so the Vmax that we're going to get because you have more enzyme contributing to that. So we're going to get double the Vmax, but the individual properties of that enzyme itself aren't going to change. Yes, so Km is half of the Vmax, so you're actually just going to stretch the graph. So your Km is going to stay the same, but that graph is just going to get stretched horizontally or vertically. For the student saying Km equals the concentration of enzyme substrate, I think that's the KD you're thinking of. But I might have to double check that in terms of the concentration of enzymes times substrate over the enzyme substrate complex. Oh, how does it happen, the graph stretching one? Because your Km is going to stay the same because you're not changing the individual properties of that enzyme, but you have now twice as many enzymes contributing to that kind of overall Vmax. So that's going to double. So your Vmax is going to get higher, but your Km is going to stay the same. So that Vmax is just going to, that's why it's just going to appear to stretch. So how can you stretch it without changing the midpoint? So you're not extending it, you're increasing, so that hyperbola is just going to kind of go higher. It's going to just reach higher on that x-axis. Sorry. Yeah, someone put up the Km is the Michaelis-Menten constant. Yes, for the one student. I think you're referring to the KD. Student wrote Km. Oh, okay. I think I get what you guys are saying. Km is not half the Vmax. Km is the substrate concentration at which half the maximum rate of enzymatic activity is reached. Yes. Someone's saying the Vmax is not twice the Km. Okay, wait. We're going to go back for a second. Hold on. So if we go back to our curve, this is going to be a constant concentration of enzyme. So our enzyme is going to stay the same, but you're increasing the amount of substrate. So as I said, the Km is, yes, that's going to be given in, oh, someone said, can you draw on? Yes, I can draw on it, yeah. So yeah, we're saying the Vmax is going to be 0.2. Pencil. So what we're going to get is, oh, this is going to be tricky. Ah! Let's do it this way. Oh. It's going to kind of come like this. So this is going to be a bit steeper. So that kind of makes sense. So we're hitting so if this is, one enzyme concentration. There we go. Oh my gosh. This is going to be 2 times. So it's just going to be a kind of steeper rate that's getting to that overall Vmax. But the binding efficiency of that enzyme is unchanged because you're not really changing like the pocket at all. So half the rate is now going to be here. Let's say this is now going to be the new half, but that's still going to be at 0.2. Does that kind of make sense? So it's still at 0.2. It's just half our rate is higher. Maybe I drew that wrong the first time. So I guess our half our V naught is changing, but that half the V naught is always going to be at that 0.2 molar. Can I erase this? Wait, let me do a better job. No. So if we continue this line up here, this is half our Km. And if we come here, oh my gosh, I'm so sorry. Our half our initial rate is higher, but it's still occurring at, here we go, our 0.2 molar. So now our half our V naught is there. But it's at the same concentration of substrate. Concentration access. Okay, I think I see you guys are saying the equation half the Vmax is misleading. Oh, okay, I think I see what you guys are saying. Yeah, so it's the concentration at substrate at which you've reached half the maximum velocity. Or sorry, yeah, half the max, half of the max Vmax. I don't know if I'm botching this. So our Km is always going to be 0.2, but the V naught, you're going to get whatever, it's always going to stay at kind of half of the V naught, but that half of the V naught can change, but our Km is not changing. Okay, yeah, I think I did draw this new graph better. Yes. Yes, so the value of our half of the V naught has increased on the y-axis, so it's a bit higher here, but it's still occurring at the same substrate concentration. So no, you're not taking so these units, like I think someone pointed out earlier, so you're not dividing the Vmax by 2 to get the Km. It's the concentration of substrate at half of that Vmax, that's going to equal to your Km. Sorry, that is a misleading equation. So Vmax 2 times and V naught 2 times, V naught equals Vmax. Someone's saying Vmax stays the same. So our Vmax, so if you add the amount of enzyme, you're going to get double the Vmax because you've got more enzyme contributing to that overall initial velocity, which is going to increase the initial velocity, which kind of reaches half that Vmax, but again, that's still the same Km. Someone says, so the Km changes only when we have a different enzyme, right? Yes. So if you have a different enzyme, or you're going to get inhibitors, which we're going to talk about next class. So to change the Km, you have to actually change the actual structure of that binding pocket. Okay, I'm gonna continue on. Sorry about that, guys. All right, so if we do the inverse of that, we have half as much enzyme is used. What is this going to look like? No changed halved. Perfect. Unchanged halved. What happens if we instead change the temperature from 37 degrees to 45 degrees? Or these two are going to be kind of the same. We decrease the pH from 7.2 to 6.5. Someone says depends on the enzyme. Yeah. And how well each enzyme works in either conditions. Yes. Oh, someone's saying KM could decrease if it denatures. So this was kind of a bit of a trick question. It was kind of just to show, yeah, Vmax would decrease too if it denatures. Yeah, so it's more just kind of saying how sensitive enzymes are to their specific environment. So as you guys mentioned, it could denature, it could inactivate it. So we wouldn't really be able to kind of look at these Michaelis-Menten variables anymore because we're getting an inactivation. But like one student did said, it depends on the enzyme. So some enzymes might still be functional at 30 or 45 degrees, and that actually might improve their efficiency. So it kind of depends, but in most cases, I think enzymes are really specific to temperature and pH, so it could actually lead to the inactivation of these enzymes. Someone said the optimum temperature for most mammalian enzymes is roughly around 45 degrees Celsius, right? And then further each increase would cause denaturation. Again, I think it depends. I think body temp is like 37, so that's probably optimum. But like in labs, some of the enzymes that we work with, like in order to denature and inactivate them, like we go up to like 95 degrees Celsius in order to do that. Some enzymes take less heat than that, some take like more. So again, it's going to depend on the enzyme itself. Someone says, how do we change KM? Or does binding affinity not change for a particular enzyme? We're going to get into this next week when we talk about regulation. So when you start adding in allosteric activators, inhibitors, and those kinds of things, then you can start changing the KM. Yeah, someone wrote inhibitors. Excellent. Okay. You just purified a new enzyme by gel filtration and affinity chromatography, assuming it's 100% pure. How can you determine the Km and the Vmax? To look at the reaction of A to B. Generally, kind of what steps would you have to go through? Rate of product formation. Yeah, so what's that rate that we would be looking at? So you guys are K1 and K2. Yeah, our V naught, yeah, so someone mentioned it. So we're looking for our V naught. And if we are looking at the disappearance or the formation of product, one thing that we would need to do is have different concentrations of substrates and then looking at those rates if we're trying to get these Michaelis-Menten kinetics. And then we can plot that. So like you guys said, we're looking for the appearance of product at different substrate concentrations to calculate that V naught. And then we can plot this into a Michaelis-Menten curve. From this Michaelis-Menten curve, can we determine the exact concentration or the exact value of our Km and our Vmax? You guys think? No. So what do we have to do? The double reciprocal Linn-Weaver-Burk plot, excellent. So step 3 would be to plot our Linn-Weaver-Burk plot, which is a double reciprocal. And then from this, we can determine the slope, which is our Km over Vmax. And if we wanted to just determine each individual value, we could look at the y-axis to determine the Vmax and our x-axis to determine the Km. Excellent. So just remember the difference between the Michaelis-Menten graph and the Linn-Weaver-Burk is if you do want to get exact values, you can't really get that from this curve. You can kind of get a good estimate, but it's not as specific. So if you do want to get specific values, which I think is going to come up in, do you guys have a enzyme assignment? Might come up in your enzyme assignment. If you want those specific values, you're going to want to do a Linn-Weaver-Burk plot. All right, moving on. From this, you determine the Km of your enzyme with substrate is 0.1 millimole. When the substrate concentration equals 0.2 mole, the rate of product formation is 43 micromolar per minute. However, when the substrate concentration is 0.02 molar, the same rate is observed. Explain using Michaelis-Menten kinetics whether or not this observation makes sense. So just looking at the numbers themselves, does this kind of make sense to us? Someone say no. Okay. Why not? Aha. I think someone saw the unit. So this is, again, what do you guys have to be careful? So someone said the rate should be higher for 0.2 because, yes, you do have more substrate. But if you look at the Km, it's 0.1 millimolar. So both of these substrate concentrations are far higher than that Km. So we can look at this mathematically. In the first situation, we have our 0.2 molar, and our V naught is going to equal our Vmax. And then if we input our second concentration, our V naught still equals our Vmax. So this is showing that we're much farther down in the curve. You got me there. Yes, careful of those units. So the substrate concentration is very high compared to our Km. So I just want to show you can rationalize that just looking at the unit or like the numbers themselves, but you can also mathematically determine that. All right. In the interest of time, I'm sorry if you guys didn't get that copied down, but this is recorded. We've been setting up your experiments to determine the Michaelis-Menten parameters. What would be the best range of substrate concentration, or to determine the rates as a function of substrate and enzyme concentration for this pair? What do you guys think? Someone's saying 0 to 1 km. Yeah, so you want to go, sorry, someone said how much funding do we have? Nice. Yeah, so you would want to go below your km or equal to your km, which is exactly right, 0 to 1, because this is going to kind of give you the best rate, because your I think it's like first order kinetics in this range. So as you add more substrate, you're going to get kind of a dependent higher initial rate. And I think the last part of, second last part of this question is, at what concentration would the rate of product formation equal or almost equal Vmax, where your V naught is only going to be dependent on enzyme concentration? After 2 km. Okay, yeah, you guys are putting it in terms of km. So yeah, you could definitely do this too. I actually put in the km for this, so I don't know what it is in terms of km. But yes, you're right. Substrate concentration is going to have to be much higher than our km. So what I did for this is, again, you're never going to like reach your Vmax. So I did kind of, let's say 1 for our Vmax and 0.99 for our approaching that Vmax for our V naught. This is going to be about 10 millimolar based off of our km value that we're given for this question. But as you guys did, you could have put in km for that and kind of determined it from there. It's like a product of our km. Again, this is one of those ones where you kind of had to sub in values, so you guys may get slightly different if you said like 95% of your Vmax like we did for the previous question. Okay. Last part of this question, what would the turnover number be in seconds if 0.2 micromolar of enzyme was used for the kinetics experiment? What about if we used instead 0.4? So which enzyme is catalytically more effective? One that would require 0.2 micromolar or one that would require 0.4 micromolar to achieve these results? So you're going to want to use the same Vmax that was previously given. But I think, yeah, you can rationalize it on your own too. So someone said 0.2 is more efficient, which is correct. So 0.2 is more efficient because you have, again, you're using less enzyme in order to reach kind of the same velocity. Yeah, so the same maximum rate. So therefore it is more catalytically efficient. Whereas 0.4, you need double the amount of enzyme in order to hit that same Vmax. And we can compare that in terms of our KCAT, where you get 3.2 kind of turned over, or substrates being converted, 3.6 per second rather than 1.8. All right, moving on to enzymes. All right, I haven't done a little poll in a while, so we'll do that. All right, so I'll give you guys a second to go through and fill out this chart on the different enzyme classes. All right. So I gave examples of these. You guys do not need to memorize these. Just kind of want to put that out there. So it's just an example if you wanted to kind of like look it up. All right, oxoreductases. They're key features of this class of enzymes. Redox reactions, yes, as the name would imply. Cool. So yeah, we're gonna have redox reactions. Our Leo says GR, so we're losing electrons, oxidation, gaining electrons, reduction. If you were looking, oh, yeah, someone said NADH and FADH2. Excellent. So if you see these kind of cofactors being used in the reaction, it's kind of a giveaway that this is an oxoreductase. Transferases, what we got? Moving one group of one molecule to another, yes, as the name would imply. Usually transferring some sort of functional group. So we see this a lot with phosphorylation, which is our kinases. We have our hydrolases. Hydrolysis, yes. So again, a giveaway is going to see if you have kind of like water participating in that hydrolysis reaction, it's going to be a hydrolase. So you need to have water present, hence hydro. Our lyase are synthases. Addition / cleavage, yes. But that's going to refer to our double bond. We're either creating a double bond or we're adding to a double bond. So it's going to be specific, like make sure for this group, because you can get cleavage in other ways, but make sure it's part of the formation or removal of that double bond. Isomerases. We'll just kind of go through these, I guess. We're going to change to another isomer. So you're not going to be changing, move functional groups within a molecule. Yeah. So your overall structure or your overall composition isn't changing, but the structure and kind of organization of that is changing. Our ligases and our synthetases. Alpha-cyclization for ligases. I think so. Joining molecules using nucleotides. So we're going to have two molecules being joined, but one of the key features of ligases is that it's going to be using ATP. So if you're using ATP to join two molecules, then it's going to be a ligase, and it's not reversible because obviously in some cases, it's very difficult to make ATP. You need a higher energy molecule, so that's why these reactions are not going to go in the opposite direction. Someone just asked, are transcriptases falling into synthetases? I'm not 100% sure on that enzyme, but I can look it up if you wanted to email me that, but I don't know it right off the top of my head. And lastly, the translocase, which I think is a recently new addition to the enzyme classes, is going to be the transport or movement of ions or molecules across the membrane. So we have our solute care or proteins. All right. Lovely. And, oh, no. Okay, practice problems. I want you guys to look at the following reactions and determine what kind of classes these enzymes belong to. So I'll give you guys a second, even though I kind of give you the first one. Someone said, what was the example for translocase? Solute carrier proteins. So these are a pretty big class of membrane proteins. Yeah. Someone says phosphatase class. So what does a phosphatase use in order to in order to kind of cleave that phosphate group? And then I'll tell you something about the class. Okay. For the first example, we have creatine, and we're going to use ATP in order to make phosphocreatine. So what would this be an example of? Transferase. Perfect. I kind of gave that too. So this is an example of a transferase because you're transferring that phosphate from that ATP onto the phosphocreatine. So this is going to be carried out by creatine kinase, which we previously talked about. So kinases are always going to take that phosphate from an ATP and add it onto a group. All right, what about our next one? We have glucose 6 phosphate. We're removing an inorganic phosphate. And if you notice, we have a water molecule up in the top corner here. Hydrolase, yes. So because we have that water molecule that is kind of leading to the cleavage of this phosphate group, this is going to be hydrolase. And lastly, we have our glycogen, and we're going to take an inorganic phosphate, our glycogen phosphorylase, and we're going to add that phosphate onto one of our glucose molecules, cleaving it from the glycogen to produce a glucose 1 phosphate. So what is this an example of? Someone goes an isomerase. For the isomerase though, is the molecular weight of that original glycogen chain staying the same, or is it changing? Something needs live. For the lyase, we would be looking at double bond. So is there any double bond that's kind of occurring? So yeah, for the isomerase, your molecular weight is changing because you are cleaving that group off, so it wouldn't be an isomerase. Transferase, yes. So that is the correct answer. So you are kind of transferring this phosphate group onto that through that process, you are getting cleavage, but it's still transferring that group, so it is considered a transferase. So this is kind of some of the different ways that you can have phosphate. So you can kind of contributing to different reactions with different enzymes. So we have our phosphate from our ATP, we're producing an inorganic phosphate, and then the phosphate here is kind of participating in this cleavage. Yeah. All right, well, we have 7 minutes left for questions if you guys have any. But that concludes tutorial for today. Thanks, everyone. Oh, I meant to stop recording, not stop sharing.